Hello there, and welcome to another edition of Calc Chat. Today I'll be your host, Jason Giordano, and we have a wonderful episode for you. We are going to be talking about two new theorems. We have Rolle's theorem, looks like Rolle, it's Rolle's theorem, which is going to lead us into what we have as the mean value theorem. Now, I've talked to you guys about a couple of theorems already. What I've been told is that there's only a couple of theorems that you guys have to know by name and the conditions that need to be met to apply them on the AP Calc test. One of which is the intermediate value theorem, which we learned back in Chapter 2. And then the other one is going to be the mean value theorem. So even though we're talking about two theorems today, this Rolle's theorem that we'll talk about kind of becomes obsolete once we talk about this mean value theorem. All right, but I want to start off, if I was in class and, well, I would have you do this exploration. And I just want to show it to you guys. Okay, so you don't need to get out your book. And I want to show you what this exploration says. It says, sketch a coordinate plane on a piece of paper. Label the points 1, 3, and 5, 3. Using a pencil or pen, draw the graph of a differentiable function that starts at one of the endpoints and ends at the other endpoint. Is there at least one point on the graph for which the derivative is 0? So the slope of the tangent line is 0. Would it be possible to draw the graph so that there isn't a point for which the derivative is 0? Explain your reasoning. So I'll kind of show you what this exploration is getting at here. It says draw a coordinate plane. So I'll go ahead and do that. It says label them 1, 3 and 5, 3. And basically the question's saying, if I draw a differentiable function from here to here, is there going to be a place where the horizontal tangent or where there's a horizontal tangent? And so there's a couple ways you could draw this graph. You know, it has to be a differentiable function. You could do something like that, in which case the derivative would be 0 right here, because that would be a horizontal tangent. You could do something like that, in which case there's 3 places where the derivative would be 0. Or you could just straight connect them, straight across, in which case every place has a derivative who's 0. And so basically what they're getting at there is Rolle's theorem. Here's what Rolle's theorem says. So every theorem has conclusions as long as the conditions are met. And here are the conditions that have to be met for Rolle's theorem. Condition number 1, you need a function that is continuous. I'm going to adjust this here. Pardon my technological slowness. So number 1, f is continuous on the closed interval a to b. So it has to be continuous on the closed interval. 2, your function is differentiable on the open interval. That means no discontinuities, that means there's no sharp turns, anything of that nature, no vertical tangents. And the last thing that has to be true, the last condition, is the y values of the endpoints have to be equal. And this is a biggie here as well. So f of a has to equal f of b. And these are all the conditions that were met in the original exploration. You know, the 2 endpoints had the same y values, and it said you have to draw a differentiable function. That means you couldn't draw something that went like this. Because on this graph here, well, yeah, there's no derivative that equals 0, but this is also, you didn't meet the conditions. It's not a differentiable function, so that wouldn't have even been able to have been drawn in the first place, okay? So the endpoints have to be the same. If you have a continuous differentiable function and the y values of the endpoints are equal, then there is at least one c on a to b, so that means one x value in the interval. Oops. One x value on the interval, such that f prime of c equals 0. Now, obviously, while I want you to copy the notes down, I want you to also hear what I'm saying and try to make sense of this. If you have a continuous differentiable function and the endpoints have the same y value, that part matters there as well. Because, if I had a graph where the y values weren't the same, right here, then certainly I can draw a continuous differentiable function, and there's not a place where the derivative is 0. All right, so that condition does have to be met. But if that happens, there's at least one x value that if you would take the derivative at that x value, you would get a horizontal tangent line or a slope of 0. That is Rolle's theorem right there. So it doesn't help you find anything, kind of like the other ones. It just tells you that it's going to happen if those conditions are met. So these first three say, can we apply Rolle's theorem for the following graphs? Essentially, they're saying, are the conditions met on this graph? Let's take a little look. So this first one, can we apply Rolle's theorem? Well, we need a continuous, check, differentiable function. This isn't differentiable, it has a sharp turn right here. So we cannot apply Rolle's theorem on this graph. No, not differentiable on A to B. So you have failed a condition. What about B? Well, this one, you could say it's not continuous or differentiable, but if you're going to say a theorem doesn't hold, you just need to state one of the conditions about why, not all of them. So I could say, no, not continuous on the interval. And the last one. Oh, it's kind of like the example I drew right up above. Interesting. Can we apply Rolle's theorem? No, because the y values of the endpoints are not equal. We say f of a does not equal f of b. If this function's name was f. Now its name is f. Hello, f. So we cannot apply Rolle's theorem to any of these. Okay. So example 1 says, can Rolle's theorem be applied to this cubic function on -4 to 1? If so, find the x-intercepts and find c values where f prime of c equals 0, or in other words, where horizontal tangents are. So first, let's answer A. Can Rolle's theorem be applied to this function on this interval right here? And, we can't just say yes. We need to state the conditions that apply. So let's think about what has to be true. We need a continuous and differentiable function. So if I look at this, every single polynomial function in the world is continuous and differentiable. You don't have to prove that's true, but you do need to state that it's true just to show that you understand the conditions. So I would say for part A, I would say f is continuous and differentiable on the interval. F is continuous and differentiable. So we've met the first two conditions. And you could say because it's a polynomial function, I don't even think that would be required. The next thing that has to be true is the y values of this function at the endpoints have to be equal. If that's not true, then Rolle's theorem, you don't know if it holds up. So let's check and see what the y values are at -4 and at 1. And I'll kind of do this work for you. I think you guys can evaluate functions. But f of -4, when you plug -4 in, you get 0. And when you plug 1 in, you get 0. Now, it doesn't matter that you get 0 both times. What would matter is these are the same outputs. Like if this was 5 and this was 5, Rolle's theorem would still apply. They just have to be the same. So since f is continuous and differentiable on this interval, and the y values at the endpoints are equal, therefore, Rolle's theorem can be applied. I wrote apples. Rolle's theorem apples. I don't think that's true. Rolle's theorem applies. Part B says, if so, find the x-intercepts and find c values where f prime of c equals 0. It's kind of, part B alone is two separate questions. Let's first find the x-intercepts. And let's go back to your knowledge of intercepts. Anytime you want to find intercepts, plug 0 in for the opposite letter. So if you're looking for x-intercepts of a function, plug 0 in for y, or for f of x in this case. So for x-intercepts, let's set our function equal to 0. 0 equals x cubed plus 3x squared minus 4x. And now we need to solve this. Well, we can factor out an x. So I took an x out. And what's left over, we can even factor more. We can find what multiplies to negative 4 and adds up to 3. So 4 and negative 1. That gives us x-intercepts of 0, negative 4, positive 1. Those are our x-intercepts. And where we're headed with this, just so you know what we're trying to do, we're going to try to sketch this graph right here. That's what we're after. We're going to try to sketch the graph of this function. And now we know it's going to hit the x-axis at these 3 values. And the next thing we want to find, well, we know it's a cubic function. You know, it's going to have like 2 humps in it. Essentially, by knowing Rolle's theorem applies, we can figure out where those humps actually occur. Instead of just drawing a rough sketch, we can pretty much find exactly where those humps are. So it says, find c values where f prime of c equals 0. Well, for x-intercepts, we set the function equal to 0. To find this, we're going to set our derivative equal to 0, which means let's find the derivative. So f prime. Let's use our power rule. There's our derivative. And we're trying to figure out where this derivative equals 0. All right, so now we have this quadratic equation to solve. And you can sit there and try to factor it, but I will save you the headache. This function just does not factor. So I could have said solve this and had you guys sit there and try to factor it, but it doesn't. But alas, we have a very powerful tool in our back pocket called the quadratic formula that will solve every quadratic equation for you. So let's go ahead and use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And then we can simplify this. You know, what I want to do is graph this. And so I want to take out my calculator and get the actual decimal values. If you were just going to go ahead and say this is non-calculator, then just simplify this and leave your answer in radical form. But I'm going to take my calculator out. You don't have to. I'm just going to give you these values. But if you simplify this all the way down, you get x equals 0.528 and x equals negative 2.528. So I want you to understand what these values all mean. Here are the x-intercepts. Here are the x-coordinates where we have horizontal tangents. Right here. This is where the derivative would equal 0. And since we're trying to sketch a pretty accurate graph, I'm going to go ahead and figure out the actual, it doesn't say to do this, but I'm going to go ahead and do it anyway. I want to figure out the y values. Like, this is where the humps are going to occur. That's what this tells me. If we draw a cubic function, you know, it's going to go something like this. These are the x-coordinates of these humps. But it would also be nice to know how high did the humps go or how low did the humps go. And we can figure that out by finding the ordered pairs. So I would take my calculator and take these two x values and don't plug them back into the derivative because you just found out that we'll get 0. Let's plug these back into f to figure out what the y values are. And if you do that, I have full faith you guys can do that on your own, so I'm going to give it to you. You get negative 1.128 and 13.128. These are the exact locations of the humps right here. And so now if I want to go ahead and sketch this graph with very good accuracy, I'm going to draw a coordinate plane over here. And put in some values. I know it goes from negative 4 to 1, so I don't really need to do much more than that. And I know my x-intercepts are at 0, negative 4, and 1, so I can put my x-intercepts there. And I also know the points where the humps are. You know, I know there's going to be a point at negative 2.5-ish up to 13. So negative 2.5-ish up to, I'm just going to estimate and throw a 13 in there. So I know that's where my hump is going to be. And then the other one is at 0.5, negative 1-ish. Right around there. And then I can draw this cubic function. I make those sounds anytime I draw a graph. And there we go. Okay. So Rolle's theorem tells you if you're going to have x values where you have horizontal tangents or derivatives of 0, okay, which is nice to know where those humps are. But Rolle's theorem really leads into a more powerful theorem. Rolle's theorem is a very specific case of mean value theorem, if you will. So Rolle's theorem leads to the mean value theorem. Now I'm going to draw a graph here, and I want you guys to draw this graph as well. I'm going to put some information in here. So, kind of like Rolle's theorem, I'm going to have interval a to b. I'm going to draw some endpoints, but I'm not going to have the same y value of the endpoints. This is going to be the difference between Rolle's theorem and mean value theorem. Rolle's theorem only applies if the y values are equal at the endpoints. Mean value theorem applies no matter what the y values are at the endpoints, which creates a whole lot more power. So you don't have to have the same y value here. And here's what's going to happen. So I'm going to draw a graph, looks like this. Right there. Okay, so here's my graph, and I want to explain what mean value theorem is going to tell us. The mean value theorem essentially tells us, I don't want to state it yet. Let's go back a second. Remember that the slope of the line containing endpoints, like if I would connect these endpoints and calculate the slope right here, if I would find the slope of that line, that's known as the average rate of change over the interval, average rate of change. So if you connect the endpoints, you get the average rate of change over the whole interval. Hopefully that rings a bell. What the mean value theorem is going to tell us is that if you have a continuous and differentiable function, now the y values don't have to be equal. You could throw the third condition out the window. If you have a continuous differentiable function, there is a point or points, just says there's at least one, we'll call that C, whose instantaneous instantaneous rate of change equals the average rate of change. So there's at least one point whose instantaneous rate of change, that means slope of tangent line, equals the average rate of change. And I'll put that into more specific vocab for the mean value theorem. But really what it's saying, if I look over here, if this is the average rate of change, it's saying somewhere along this graph, if I would draw the tangent line, it's going to be parallel to this. It's going to have the same slope as this. It's going to be somewhere, I'm just going to estimate here, somewhere like here for this particular case. If I calculated the slope of the tangent line right here, that slope is the same as this average slope over the whole interval. That's all it's saying, is that there's a point whose instantaneous rate of change equals the average rate of change. And that's really what's happening on Rolle's theorem, right? If you have the same y value, look back at this original graph. If I took the average rate of change on the interval, the average rate of change is 0. And all Rolle's theorem says is there's a place in the interval whose derivative equals 0. So Rolle's theorem is a very specific case. It helps you identify horizontal tangents, but this is much more powerful because you can apply this to a problem where Rolle's theorem applies to. But to put this into good vocab, if f is continuous and differentiable on an interval. And that's all that has to be true. You know, anytime you talk about a theorem, you have to think about the conditions that have to be met to uphold the theorem. And this is all that has to be true. You need a continuous differentiable function on a closed interval. That means endpoints included. Then, there exists a c, a number c, in the interval. Notice it says in the open interval. This is important, so not at an endpoint. So there's a number in the interior of the interval such that f prime of c, so that's the slope of the tangent line at c. This is the instantaneous rate of change. There's some c value where this derivative is equal to the average rate of change over the whole interval. Well, think about what we did with average rate of change. Average rate of change is just slope formula. So on the other side, we're going to do the slope formula over the whole interval. F of b minus f of a over b minus a. So what they're saying is there is a c value in the interval that if you would take the derivative, it's going to equal the average rate of change, or the slope formula. That is the mean value theorem. Mean kind of meaning average. You know, so you have average rate of change, average value theorem. There's a value that equals the average. I'm just spitballing. All right, two last examples. Given this function, square root of x minus 2 on the interval 2 to 6, find c such that f prime of c equals f of b minus f of a over b minus a. So in other words, I'm trying to find a value where the derivative is equal to the average rate of change. So if I don't know the average rate of change, that is probably a great place to start. I want to find the average rate of change of f over the interval 2 to 6. So let's go ahead and do that. So let's find f of 2 and f of 6. F of 2 is 0. F of 6 is 2. So the average rate of change is 2 minus 0 over 6 minus 2, or 1/2. The claim is that let's find the c value where the derivative would also equal 1/2. So if we're talking about derivative now, let's find the derivative of this function. So I want to find the derivative of f. I'm going to do that over here. I'm going to rewrite that as x minus 2 to the 1/2. And now I have to think chain rule, because I have inside, outside function. So let's find the derivative. So 1/2 comes out. Inside stays the same, reduced by 1, times the derivative of the inside, which so happens to be 1 on this case, but you know, I don't just want to forget about the chain rule. If this was something other than x, we'd have to multiply by something. So here's our derivative right here. So think about what we're trying to find. I think it's important that we understand what we're after here. I want to find the x value, where the derivative equals 1/2, the average rate of change. So if I want to know where does this derivative equal 1/2, set your derivative equal to 1/2. Don't plug 1/2 in for x. I want to find x that makes the derivative 1/2. So set your derivative equal to 1/2. And we can go ahead and multiply both sides by 2. That'll get rid of these 1/2s here. So 1 equals, and I can write this as 1 over square root of x minus 2. We just have some algebra here. I basically multiplied both sides by 2. And now I'm going to multiply both sides by the square root of x minus 2. And then I'm going to square both sides. So x minus 2 equals 1. So x equals 3. It says find c, so I might take that x and just say c equals 3. I think it's important for you guys to see visually what this means. All right, I want to graph this function on 2 to 6. I want you guys to see exactly what it is we just found. So I know it's at 2, 0, and 6, 4, no, 6, 2 here. And it's the square root function, so it looks something like this. So what I did in this problem, I first found the average rate of change to be 1/2. Like if I take the slope of that dotted line, I get 1/2. And I'm after where in this interval would the slope of the tangent line also be 1/2. And we just found it to be at 3. That's what we found. So if I take the point on this function at 3 right here, and I draw the tangent line, notice that it's parallel to the average. That's what we just found. I think it's good to see visually. I'm going to have you guys go ahead and pause it and try example 3. You know, as with any notes, I think it's good for you guys to try on your own. So go ahead and pause this video. Now, push pause, click, and I'll see you back in a second. Okay, welcome back. So I'm going to put the answer up here. You guys can see how you did. So it says, given this function, find c that satisfies the mean value theorem. Mean value theorem says there is a c value in the interval whose instantaneous rate of change equals the average rate of change. The first thing I would find is the average rate of change. Find the y values at the endpoints and then do slope formula. The average rate of change from -1 to 1 on this function is -1. I'm trying to find the x value on the derivative that makes the derivative equal -1. So I took the derivative, set it equal to -1. Any equation that you want to solve above a linear equation, above x, set it equal to 0. Some of us messed that up on the last test, so add the 1 over. And this one does factor, or you could use quadratic formula. It does factor, and you get -1/3 and 1. And you might be tempted to put both those answers. However, right here, I said not at an endpoint. We need values that are in the interior of the interval, not at an endpoint. So since 1 is at an endpoint, we aren't going to include 1, just -1/3. Just little things to think about. I bet that tricked some of you. All right, you have some homework. Enjoy Rolle's theorem and mean value theorem. I am signing off once I figure out how to sign off. It says push escape, and then it says push stop.